Karson and I prepare kind of a deep dive on the challenges that we are seeing on TCAD modeling silicon process technology. And just the outline that of the slides that we have today, we'll talk about some background on what are the expectations for this deep dive, and then where we stand on modeling on semiconductor processing, right? I think what are the main challenges that TCAD face when trying to attack these very complex problems, right? And then we will focus on these areas that we are mentioning here, litho and patterning and etching and deposition. So this is, I think that is what we prepare a few slides to kind of lead the discussion on that. But I think when Victor, when we chat with you, right, it was kind of an informal talk, what you said. So we didn't put a lot of the details in terms of technical stuff, but it just meant to be more like a conversation and a discussion with everybody can chime in and participate or ask the questions. And then we throw at the end some slides on there is kind of this explosion of AI and machine learning these days, and how we see that fit in the applications that we have for TCAD. And hopefully we get to that session, but let's see how we are doing with time. I think the key thing will be basically to kind of go over the discussion of the technical challenge of these focus areas. Okay, so in terms of the background and expectations, TCAD over the years, right? TCAD has been, in the industry, for more than 30, 40 years now, right? It has been evolving with the industry, and it has been an essential part or essential component to speed up the technology development and the learning, right, on the silicon manufacturing processes. So we'll focus today on those challenges that we are facing, as just mentioned, on those two areas, and just to kind of keep this be clear that we are not going to be discussing anything about device and transistor mechanical stuff or die package interactions or yield, right, which are also important aspects of TCAD, right? So I think based on the feedback that we got initially, we chose those specific areas that I mentioned in the previous slides. Okay, so sorry, is there a comment?
Yeah,
some noise, right? Okay.
Okay. I suggest that we mute us so we don't.
That's fine. I'll keep going. One of the key challenges, right, in TCAD is to keep pace with the technology evolution, right? If you look at the roadmap, this is the Intel roadmap, right, starting from the 90 nanometers all the way to where we are today, entering into what we call the Armstrong era, in which now two very significant innovations are being introduced, right? One is a nano ribbon, and then the other is this backside power delivery architecture. So these two are going to be first in the industry when we get with the Intel 28 nano Armstrong technology. So the key challenge here of TCAD is to keep pace with this pace of innovation, right? So this is every 2-3 years is everything it changes for us. So when we think of our models, we need to keep in mind that what is the reuse of those models, right? That is one of the challenges that we have. The package technology has also been evolving as well. And in fact, when you look at where we were with packages, with our packages, let's say, 15 or 20 years ago, it was pretty simple, right? The main function was to provide an interconnection between the motherboard and the silicon. That was the main function of the package. Today, that is much more complicated, right? We have all these heterogeneous integration with multiple dies in the silicon in the package. We do have pieces of silicon embedded in the package itself, like in the case of the bridge technology that Intel introduced, and a lot of the processes that were part of silicon, right, like etching, depositions, technologies. they never play a role in packaging. Today, they are also they have to be considered, right? So that's how packaging is also getting more and more complex, and TCAD is also starting to play a significant role on package technology. Going into the challenges, right? The multi-scale is one of the key things, right? As we know, we build our things on 300 millimeter wafers, but everything that we worried about is on the micron or nanometer scales, right? So there is a significant bridge that we need to cover in the simulations when we try to understand what happens on the wafer. So there are basically 8 orders of magnitude in these scales. So a lot of the process that happen at let's say at the reactor scale, right? Let's say for the deposition process, that has impact on wafer at the nanometer, the tens of nanometers that we need to understand. That's one of the key challenges that we face. The other is the complexity and the need for multi-physics and the super broad set of skills that is needed in TCAD. Like if we look across our department, right? In TCAD, I mean, we basically had people from almost all the physics and engineering disciplines, right? You list them here on the left, the different scientific disciplines, and the expertise in terms of the technical expertise that we draw from those disciplines, and where we end up in terms of models, technologies, and tools, right? And then in addition to that, now we have data and machine learning, right? AI and machine learning that is also coming into play to play a significant role. And the last one is material, right? So basically, it's multi-scale, multi-physics, and today multi-materials. If you look at the evolution of the uses of materials in process technology, you compare what we were on the 90s, where only a handful of materials were used in our process. But today, pretty much the whole periodic table is being used. I mean, this is a chart that we have used many times to illustrate that. And the explosion really is not only in the number of materials, but when you look at the combination in terms of alloys that you can create with these materials, is just significant. I mean, the amount of analysis that needs to happen to kind of optimize the material is super complex. So those are the 3 key challenges, right? Multi-scale, multi-physics, materials. And now when you look at this is a simplified way of looking at our process, but every time that we need to, the way that we do wafer processing, as you know, we do layer by layer, right? And more or less that involves a deposition. After that, there will be a polishing step. Then we do litho. And then after that is etch or implant, depending on where you are, right, in the process. Ash and cleans, and then do some annealing, right? And then it goes back to the next layer. Now, if you look at all the chart on the right, this is the number of process steps that we used to have in 22 nanometers, 14 and 10 nanometers. And you can see that by the time that we get to 10 nanometers, we basically double the number of steps, right? So essentially, all this process is repeated many, many more times. And sometimes even to create a single layer, you need to do this process many times, right? If you are doing, like a double litho etch, or these tricks that that you cannot do a single print with your lithography technology. So that is the complexity that that adds to the complexity. So in essence, if we want to have a digital twin solution, ideally what we want is to mimic all these steps for every steps and layers and predict what will happen in the wafer at the end of the process. That will be the ideal digital solution. Now, every step in this cycle involves a super complicated physics, right? That it spans multiple areas and scales, and the process. This is a multi-scale part of it, right? It happens at the wafer reticle length scale, but the impact is at the feature size, a nanometer, tens of nanometers scale today. And is multi-scale, multi-physics, and also the many materials that play a role into all these processes. And then, I said, we said at the beginning, right, in the next slide, we will focus on some of the TCAD challenges that we face on some of these steps: deposition, etching, litho, and patterning. And then, I mean, the last thought here is that generating a digital twin for each of these steps are significant milestones toward the full physics-based simulation of the full process. Essentially, I mean, if we take a step by step and we can generate a digital twin for each of these steps, that could be, each of these is a key milestone in our minds. Okay, so maybe Karson, I think you'll cover these next slides. Let me know when you want me to move, how you want to move.
Okay, so there's two slides here, one on deposition and etch, but in reality, the challenges we're looking at, from high up, look the same, and so these two slides could be kind of generic to both processes. So, but just to start off talking about deposition, the deposition surface chemistry is getting more and more complicated. There's multiple materials present during any deposition step, and you have kind of a wide variety of potential precursors, and precursors now include inhibitors where you want to block the surface. So one of the main tools we use to study chemistry in these situations is density functional theory. Where density functional theory is at right now, you look at one substrate at a time and one molecule coming in. The plot over on the right kind of gives a demonstration of how we use it, right? If you look at the reaction coordinate versus an energy barrier, you look at each material and each inhibitor molecule or precursor molecule, and you look at what you kind of throw them all in there, simulate them all, and see where the barriers are at, right? Inhibitors, you want low barriers so that they stick to the materials that you don't want to deposit on. For precursors, in those situations, you would want a high barrier if you don't want it to stick. But you just basically throw everything in there and look at everything and rank lists for experimental analysis, kind of to reduce parameter spaces. Now, if you go to the next slide. Now, again, like I was saying, it switches to etch, but really this is just continuing the same story. So DFT is great at looking at one reaction at a time, but really the real structures, first of all, they're amorphous. There's very few real crystalline materials that you work with in our domain. And there's also imperfect material interfaces, right? You're not always just looking at a transition from one material to the other in one atomic layer. And so you have to come up with systems or tools, techniques, simulation techniques that look at much more complicated systems, many more atoms, so you can actually simulate amorphous materials. You have to look at all of the different types of surfaces that can appear in an amorphous material, right? A crystalline material, you look at one surface. Amorphous, you can have many different types of reaction sites. And one of the new tools that we're exploiting for this is the neural net-based MD methods, where the neural nets are used to train force fields. And now you can go up to maybe thousands of atoms and look at multiple materials at the same time. I list some of the things we look at here: amorphous systems, melt quench, and you get more statistics about the different surface sites. But the real challenge, if you go down to kind of the lower right, and you look at a real structure, right, with three, like our gate all-around structures, where you have, say, 3 silicon channels, you're actually trying to run reactions that are selectively doing something for all the different materials here, and just throwing a bunch of materials and reactions, like I was saying in the previous slide, at the problem can help you understand some things. But really what we need to be able to do is simulate these reactions in the real structure, where you're looking at this entire transistor device at the atomic scale and understanding all the different surfaces, all the different potential reactions for each molecule, inhibitor, whatever you're looking at coming in. And we're not there yet. And that's one of the things we strive to achieve is how to do the real structure, all the materials in one simulation. So that's all I had for that.
Okay. So I mean, I feel free to kind of chime in on the discussion, right? If you have questions or comments to add. We'll move now. The next slide is talking about litho, and then a couple of slides later on patterning. On the litho side, I mean, basically what governs everything is a Rayleigh equation, right? Essentially, the feature that you want to print is equal to some constant times the wavelength and the numerical aperture. And certainly what you want is to bring D as small as possible, right? So that's so the way you can do it is by reducing your wavelength or increasing your numerical aperture. And then you need to play tricks with K. I mean, on the left here, kind of listed a few things that are happening. Like, for example, we all know the industry these days is moving increasingly into EUV, adding more and more layers with this technology. So basically, it's a 14x improvement over the standard, 193 nanometer technology that has been used for a very, very long time. And the challenges we are facing here now are mostly are basically stochastic issues, right? So EUV, you don't shoot as many photons as you can do with the old technology, and that leads to more stochastics issues, right? And interactions with the photoresist and things like that. So this is basically where there is a lot of activity and a lot of needs in terms of understanding how these stochastics impact what we print in the wafer. So NA is another one. So today there is a move again to move to point. I think it's 0.55 NA systems. I think there has been a lot of press recently with Intel getting the first ASML system with to enable high NA. And the challenge there is a development of new photoresist materials, right? So with the depth of focus being different, you need thinner materials really to print, and that basically has issues in the generation of let's say secondary electrons that are responsible for all the reactions. One of the sources of reactions in the photoresist materials, and then there is a need also to bring underlayer materials that basically adds another set of materials that need to be added and need to be engineered, right? And then these are the two key things, and then the rest, with K1, that's what we call the rest, right? And these are all a lot of tricks that people play to improve that constant, like a OPC that has been in the industry for a long time. And also, I mean, certainly photoresist materials plays a role, process etching, hard mask, everything that, all the things that can be done on wafer also help to improve K1. I mean, the chart here on the right kind of illustrates, where with all these tricks, where is the minimum K1 that we can achieve, around 0.25 here. And what happened, right, with our lithography, right? If you are still on 193 nanometers, at some point you are below that K1 line, And then the only way that you could print is to do multiple passes, right? That's basically what says require pitch division, like a litho edge or litho edge, different processes to enable that. And then as we move to EUV, then we are back in here, right, above that line. And then you can do in the same layer, you can do a single pass, right? But as you keep shrinking things again, then you start getting closer and closer to your limit in terms of the tricks you could do. And eventually, you know, we are hoping that when we bring high NA, then we are going to be right back above the line, and doesn't require all these expensive tricks like a pitch division and things like that, right? These are the tricks, right? If you need to get here with pitch division, basically what pitch division, what it does is you do a backbone structure. I mean, this is kind of a simplified schematic of this, in which you double your pitch, for example, right, or you quadruple your pitch if you want. Then you do a conformal deposition. You leave these spacers here. And then you etch your backbone material, and then with that you kind of effectively double your pitch. You can now transfer that half pitch patterns to your wafer. And if you want to quadruple your pitch, then you basically repeat the process again, right? And the more I mean, the more of these steps that you need, the more layers that you need to do, right? So adding all these extra layers is a lot of complexity. That kind of goes into that a few slides back. The number of process steps that we have in 10 nanometers versus 14, for example, the doubles has a lot to do with this thing. Now, doing this, you really want to avoid doing this, right? Because that increases all the process complexity. It requires more masks, and that adds to the cost and the complexity of the process. But one of the other problems that it has is a large source of variation, right? So when you do things like that, then you start having issues with one line, some lines being of different width at other lines, and then that also has implications on performance, right? Because you need to account for all these extra variation that you are introducing in the process. And in terms of patterning, the things that we worry about are edge placement error. So this is basically as we get while we are printing smaller and smaller features, things are getting closer and closer. And then registration errors playing a significant role, right? These are kind of, deformations of your grid, if you want, right? And there are process tricks that needs to be done to overcome the problem that, again, bring more complexity. This is what happened, right? If you do not control that, eventually when you bring a via on top of a metal line, this via has to land on this metal line, but is landing because of a registration problem, is landing on the side and is kind of shorting the next line, right? This is the edge-to-edge problem. Line collapse is another problem. I mean, as we got into narrower lines, the aspect ratio gets worse, and these things are super flexible. I mean, the ILD materials, that low-K ILD material we use today are mechanically not that strong. And when you do etching process and all that, let's say for a wedge process, you have capillary forces that will pull this structure together, and eventually will touch each other and collapse, and then they cannot be. I mean, they stick together basically, right? And that's it. You cannot separate them. That is one of the problems, right? There is a nice paper that put a reference here for those of you who are not that familiar with this problem, but this is something that we are seeing more frequently these days. And the last one that I have here is basically line edge roughness or line width roughness. So these are basically undulations of the lines, right? If we print straight lines, you can see as you go down into your pitch, that means these lines are narrower, then eventually you get into this kind of instability, right? It's a mechanical instability, and then you start having what we call wiggling or buckling of the lines. And then you can see you can control that with different resists. I mean, by the way, the mechanical is not the only driver for this. There are some other etching plays a role. The pattern in itself, right? How you print the lines and the variations in your litho process also is important. Like the stochastics will play a role here too. So you can modulate this problem by getting better resists. But this is certainly a big problem, right? And that is one of the problems that is preventing us from sometimes going into smaller and smaller pitch. This needs to be controlled, right? And the hard mask that we put on top of these things tend to be very compressive. That is what brings that brings the mechanical aspect of that in terms of buckling, right? Those compressive hard masks tends to will try to they will buckle, right? And unless it can be constrained by the line underneath, but the line if the line is not strong enough, then it will basically create this buckling phenomena. I think with that, that's what we wanted to say on these processes. So if there are questions, we can go directly into the next slide, which is AI, and leave the discussion for later, or if you want, right? That we can keep going as.
Let's, Daniel. It is maybe good moment to pause and invite the audience for to ask questions. I ask you two questions at this point, and maybe this question will lead in your next part of presentation. When we talk about digital twins in the context of digital twins, we at least envision very dynamic updates of physical process based on digital twin, in this case TCAD. In other words, the digital twin should operate real time or quasi real time. And for my impression from this presentation is that the state of the art is far from the real time modeling. So the time scales are very different.
Well, that I think that is true. I mean, the way that we have been basically approaching TCAD is more not from a digital twin perspective. I think this is a good discussion to have, right? And it's good that there is all this effort to try to bring this into that real time type of thing. I think that, and Karson, you can chime in also, right? But where we are at with the state of these tools, right? At least purely from if you want to just do the physics, right, and mimic the physics in a digital twin, I think it will be pretty hard to do it real time, right? I mean, I think we should try, but it's a challenge, right? That's one of the challenges that we have. Karson, I don't know if you want to add something there. And that is what we see, perhaps, the next area is the AI and machine learning, right? That's where we see that there could be an opportunity for those areas in digital twin.
This is what I meant, that maybe this question leads in next topic.
Leads into the next, correct, right, yeah, exactly.
And we have two questions, Ganesh and then Sadas. Ganesh?
Hi, Daniel, great talk. I fully agree with you on multi-scale, multi-physics modeling. I had two questions, if I may. First is, to what extent are continuum models useful? Are they still useful? I know you talked about surface phenomena, surface tension causing line collapse, for instance. That is a pure continuum model, and Karson talked about basically molecular scale models. To what extent are continuum models useful generally in process modeling? And second is, there is a perception that for many of these processes, the physics are well understood, tool vendors, for instance, claim that unit process models are routinely used. I'm quoting a word exactly that's been quoted. What is your opinion on that?
Yeah, I think there is a bridge that we need. I mean, there is a bridge between the atomic scale, mesoscale, and the continuous scale, right? And I think you need to basically use the right approach depending on the problems that you are solving. I think you want to really use the simplest technique, right? That you can have. Let's, for example, take that line backlink problem, right? One way that we look at this, at least to understand the mechanical aspect of it, right? Like I said, there are some other aspects that are related to more to lithography itself, but the mechanical aspect, right? Let's say you have a hard mask on top of each line, and we had been kind of, successful at least on some control experiments to match what we are seeing on wafer by just considering that thing of, like a beam on an elastic foundation, for example, right? And that is a clear example of something that is small, but you could still use some of the techniques that we see, for continuum mechanics. Now the question is, how you model the material. That is the aspect that is that when things get trickier, right? And from there, we basically need to do some understanding of the material itself, right? Do some MD and try to back calculate some properties that we could put in the continuous model. So there is that bridge that needs to be crossed, right, between these different scales. And certainly you can do that also with calibration if you have a lot of data, right? And that perhaps is where, going back into the next slide, the AI or the machine learning discussion plays a role. I let Karson also to comment. I think he has a lot more experience than me on the. He has talked about DFT, and maybe Karson, you want to add from your side, your perspective on that.
Well, I guess when you get into the multi-scales, it really becomes a problem-dependent issue. Some of this line collapse stuff, but Daniel's saying you can handle it with continuum scales, but atomic, if you want to look at feature style issues like, in dep or etch, if you want to look at pinch off or undercut or micro trenching or something, you actually have to know the chemistry involved with that ahead of time. So whether you get that empirically or by some atomic scale simulation, you have to have it. And I guess that's why I was stressing that we need atomistic type modeling at a feature scale to moving forward.
That's it. Daniel, do you want to? Sorry.
No, unless you have any other more specific questions, I'm just that's my general answer to that.
Maybe I don't want Anna Sadashivan and Jim have hands up. So I just real quickly, the second point was that there is a feeling that these physics exist, they're used routinely. Do you agree with that, or what is your opinion on that?
I'm sorry, say that question again.
So vendors, let me help Ganesh. Vendors like LAM, Applied Materials, they often say they are done with physics-based models. They have all models they need to, and they're happy with state of the art. Correct, Ganesh? It's what is the question? And we, not everyone in this audience agrees with this.
Thank you, Victor. That was my question.
So okay. Daniel, Karson.
Yeah, I got it, Karson. Maybe Karson, you want to take that? I think it's more on your areas.
I guess I'm sorry. I still didn't quite understand. You're saying that not everyone agrees that the physics of these problems are solvable, or what was that again?
Yeah. Okay. How to say it? So we are trying to define the technical scope of Manufacturing USA Institute. That is one of things. And when we go into technical details, and for example, Ganesh insists that multi-scale physics-based models is number one challenge, or maybe number two, one of the top challenges. But some vendors say, well, we pretty much done with this. We have sufficient models that help us to develop equipment and process. That's pretty much it. And so, to what extent we should emphasize the physics-based models for processes?
Well, I guess we're kind of combining two things, right? What kind of simulation techniques you need going forward, and what vendors say they have. It sounds like you're combining those two, and vendors will say they have a lot of things, but when the rubber hits the road, they don't, and they don't have simulations for exactly what we're doing in-house. So I think the summary is that the things we're talking about here in this presentation are still not there yet, and in particular, feature scale atomistic. We need to go there. We need that, and we're striving. We're going to get there, but it's not there right now. And I guess it doesn't really matter what vendors say. Vendors talk about capabilities that are highly empirically based. You have to have a lot of data to actually do what they're saying. They may have it for some particular process, but they don't have it for the new things that are not there yet.
Yeah, this is what I thought. So it's very process specific, material system specific. You change something, you need to start from zero. Actually, yeah, it's my feeling. Let's move on. We have Sankar already appearing on the screen. Sankar.
Yes.
Sadas. I'm sorry. I started to confuse your first Sadas. Sorry. I don't know why I started it.
No problem. I have actually two questions. The first question is probably for Karson, and the second question is for maybe both. I was kind of listening to what you are saying, and I'm trying to see what is actually different this time around, because there have been attempts before, as you guys are aware, since the 1990s and 2000s, to be able to do different aspects of this. Is the process technology thing was, Daniel, you articulated that the complexity, the number of steps and number of materials and all that. But what is different this time around? Why do you think this is solvable? Is it because the one thing I saw new was the neural net MD that Karson spoke of? So why do you think it can be solved, or do you think it cannot be solved? That's the first question.
Okay, well, hi, Sasvan, long time no see.
No problem.
So the neural net MD stuff is real. We can do that now, right? We can do thousands of atoms. We can do multiple material interfaces in the presence of a good portion of the chemistry that's going on, right? But the timescales are still a little low. You can get information, but you can't do it at the timescale of a real etch process or a real deposition process. But given, I hate to use the term AI. I don't like that, right? We used to call things SVD, PCA, neural nets and stuff like that. It all gets lumped into the one. And AI usually is used in the concept of referring to data mining, which is not what we're doing. We're actually using neural nets as AI for predictive things. Anyway, I'll get off my soapbox for that. But you can see that you could get somewhere where you can actually do this, but just the path to get there has not been completed yet, right? That has to be hacked away. And there's new stuff coming up like on a weekly, monthly basis now that we can try and make advances with. It's, we'd like it to move faster as we get into next generation processes. But, there's work that needs to be done. I think how to hack the path forward, there's a lot of options. I don't know the best pathway yet, but we need to get there, and I think we can.
Yeah. So that's even good to see you again. If I can add one thing, right? I mean, I think it has been a long ways, right, with these atomistics models. And actually, well, you kind of pioneer that work over here, right? You remember when you started with this, right? There was a handful of cases that we could solve. Today, that has been, I mean, like Karson is saying, right? That we are very much, that is becoming mainstream now, right? Across the board in TCAD, and we are now solving much larger systems. But I think, like Karson said, we need more, right? We need more. I mean, if I were to make an analogy with what like a standard continuum methods were, like a finite element in the 80s, right, or 90s, where people were solving thousands of nodes, and now we are solving billions of nodes, right? I think that's the next evolution we need in these tools, in my mind.
Okay, so thanks, Daniel and Karson. So can I summarize it, because I know what Victor and Ganesh asked before, so I just want to tie it. Is it fair to say that the machine learning methods are one of the biggest enablers, but the process and the material complexity is increasing faster than what machine learning models can do? Is that a fair summary of what you're saying, or did I misinterpret it?
I don't think that we said that. I mean, I think it's true that the process. I just kind of rephrase it a little bit, so that's even. I don't think we said that machine learning can do. I think certainly you are right. The process is getting super complex and a lot more complex, and the features are much smaller. The material complexity is super complex. I don't think that we said that this cannot be solved by machine learning. I mean, I think you are talking about specifically using machine learning potential for MD, or you are talking about machine learning in general? In general.
No, I'm talking about digital twin, because the thing about digital twin is that you need to apply the scales. That's the reason I was trying.
Right. I mean, I think I don't think we can claim that you cannot do it. I mean, I think we need to let the process go and see how far we can get. Right. I mean, this is starting now. I mean, if we say we cannot do it, then there is no need to have this discussion, right?
But I wanted to.
So we are very optimistic about this. Yeah.
I know the answer, but I was trying to see what your perspectives were. The second question is ties into this is you are already ahead of a lot of the people in terms of what you can do. What can external agencies or teams like the one that Victor is leading and Ganesh and all, how can they be useful to you? Because you have access to data, you have access to computing at scale. So how can, I mean, I am on the different side of the table now. And what can teams like us help with?
Yeah, I think I have that. Okay, Karson, you want to go ahead.
So specifically there, just again, to answer a little bit more about your previous question, I think the AI machine learning stuff is actually catching up with the physics and is on the cusp of being able to do what we need to now, finally.
Okay.
And with that said, there's tens, maybe even hundreds of different ideas out there of how you could use neural nets to train force fields for MD, or neural nets to speed up DFT calculations. And, it sounds like just dumping a whole bunch of things on the outer community, but we need other people to figure out to narrow that parameter space, so that, because we don't have resources to test 20 different methods for training DFT to, solve bigger problems. But, if people can get PhD theses out of it and identify the top ones, that's what we want.
Okay. Then the
So
second.
that's when I jump ahead a little bit and posted. I mean, I put here the
No
last
problem.
slide that I have. I jump basically over the AI and machine learning technique. But let me since you brought that, let me quickly go through these three last slides.
Please.
On the machine learning, right? I mean, a lot of people are focusing on these physics informed neural networks. I mean, that is, I mean, I think it works for some specific cases, but it's not clear how well they are going to work when you have multi-system, multi-scale methods,
Yes.
right? We are not very optimistic about that. At least that's my personal opinion. But I think that's an area that people should kind of explore. The other two things that people are doing, and I'm going to go this pretty fast, right? You guys will have the slides. But the other thing that people do, and we do too, is just train a model, train a neural network, right? I mean, the previous one, this is a forward process, right? There is no learning here. But here is you basically run a bunch of simulations, then you use those as your data to train a model, right? And that is something that is being done. People are doing. We are doing that, right? And that is one thing that could be explored, right? That, I mean, I think as I mentioned how this thing can help. Maybe that is an area where how we can speed up these things. And the last one, which is an interesting thing that we have explored this in some cases, is what if we use, in terms of using just hardcore data, right? What if we use input data from a physics-based model into the neural network and then train that? But by doing this, you could have access to some inputs that you don't have. You cannot measure directly, but some physics-based model can give you that input. I don't think people have been talking about this too much, and I haven't seen anything about this. But this is another area that could be pretty interesting and new for exploration. And then with that, I just put my last slide here, so that's go ahead.
Yeah, dots used to do something similar to your previous slide.
Okay.
Whether it was using physics-based model. Okay. No, but this is good. I agree with your statement. So, in terms of help, what could teams like this help you with?
I think Karson answered that, and there are a few other thoughts here, right? Keeping improving the multi-scale, multi-physics. I think the materials models is another one that I see that we need to that area is still kind of in its infancy, right? It needs to kind of evolve to very large systems.
Yeah. So if I understand correctly what Karson said and Daniel adding, I mean, they are too busy to develop in-house models to support the product lines, and they don't have time, resources, and it's beyond their scope to explore it broadly. And it is what we could do and maybe should do. Yeah, it's good. It's very good outcome of the discussion. It's a very good outcome of the discussion. Okay. So Daniel, so we let you finish, and after that, have final discussion.
Yeah, I think we are pretty much done. I mean, okay. I think we cover more or less all of these bullets here. I think I want to, if I can finish with that wisdom, words of wisdom from Gordon Moore. I mean, basically that we were doing right. We need to delay forever. We keep doing that.
Yeah. Very good, very good. Thank you very much, Daniel and Karson. And we have another question from Jim.
Jim has a question.
Yeah, I was prompted to raise my hand because from what Karson described, it sounded like you need high-performance computing. Now, I don't know if that is, let's say, Sadas indicated that you do have large-scale computing in-house, but maybe it exceeds your computing requirements exceed what you have readily available. This might be something to be identified in the Manufacturing Institute that Victor is leading a team on, or SRC is leading a team on. It strikes me that the Department of Energy, all the national labs have a lot of activity in scientific machine learning, physics-informed neural networks, obviously materials and chemistry, application developments. I would say, Daniel, that a lot of the physics-informed neural network activity has been for multi-physics and multi-scale application drivers. So, and I can certainly help identify connections for you to work, at least talk to the groups that have been involved. There's some people here at PNNL, Pacific Northwest National Lab, and at Sandia that have been involved in some collaborations dealing with scientific machine learning that may be relevant for you. So
that would be great. Thank you.
Okay, thank you.
Ganesh?
Just want to add a comment. I had one slide, a benchmark slide on physics-informed neural networks in my presentation last month. And my experience is exactly what Daniel said. Ultimately, you need quadrature. When you do quadrature, whether you use neural network as your approximating functions or Lagrangian shape functions, they end up being a quadrature problem and matrix solution problem. They don't become any different. That's my experience on a very simple benchmark problem. I'll share that with Daniel. So I fully agree with what Daniel's assessment is.
Yeah, thank you. The way I think of this is like, do you remember the old meshless methods, right? That you throw a bunch of points. I mean, I kind of think of the same way, right? For this.
Exactly the same way. It's not any different. It finally comes down to quadrature, and that's where the bottleneck turns out to be.